Today we're diving into one of the most important security concepts every modern web developer should know. OAuth 2.0 with PKCE, that's proof key for code exchange, pronounced PKCE. On the screen right now, you're seeing an overview of the PKCE flow. Don't worry about every detail just yet. This is just to give you the big picture of how the pieces fit together. And just so you know, throughout this video, I'll sometimes say PKCE instead of PKCE. It's the same thing. I'm just using the easier pronunciation. If you've ever wondered how apps like Gmail, Facebook, or your favorite SaaS tools handle authentication securely without ever storing your password, you're in the right place. By the end of this video, you'll understand exactly how PKCE, or PKCE, adds an important layer of security, and why it's absolutely critical for modern single-page applications. Stick around, because I'll walk you step by step through this flow using an interactive visualization I built, and share some real-world implementation tips that most tutorials skip. Let's start with the basics. OAuth 2.0 is an authorization framework that allows applications to access user resources without handling passwords directly. But here's the problem. Traditional OAuth flows weren't designed for public clients like single-page applications. Why? Because SPAs run in browsers where you can't store client secrets securely, code can be inspected by anyone, and network traffic can be intercepted. Enter PKCE, proof key for code exchange. It's essentially OAuth 2.0 on steroids, specifically designed for public clients. PKCE adds cryptographic proof to OAuth. Even if an attacker steals the authorization code, they can't use it without the original code verifier, which they don't have. PKCE uses SHA-256 hashing to create a one-way mathematical relationship between the code challenge and verifier. Watch how the same attack that succeeds against traditional OAuth completely fails against PKCE-protected systems. PKCE doesn't just prevent code interception attacks. It provides comprehensive protection against multiple attack vectors that target OAuth implementations like code injection attacks, CSRF on redirects, and malicious app code theft. Think of PKCE as adding a secret handshake to the OAuth dance. Even if someone overhears the conversation, they can't complete the handshake without knowing the secret. It's not just an improvement, it's essential security for modern applications. Before we dive into the flow, let's meet our cast of characters. First, we have the user, the person who wants to log in. Then there's the SPA, your single-page application built with React, Blazor, WASM, Angular, or any other framework. Entra ID plays the role of Microsoft's authorization server, though it could just as easily be any OAuth provider. And finally, we have a couple of APIs, the protected resource servers that hold the data the user is trying to access. Each one has a specific role, and the beauty of PKCE is how they work together seamlessly, without any single point storing sensitive secrets. Here's where the magic begins. When a user clicks that Sign In button, your SPA doesn't just redirect them immediately. There's some important crypto work happening first. Your application generates two things: code verifier, a cryptographically random 128-byte string. Think of this as your secret key. Code challenge, a SHA-256 hash of the verifier, then base 64 URL encoded. This is what you'll send publicly. Here's the brilliant part. The challenge is derived from the verifier, but you can't reverse engineer the verifier from the challenge. It's a one-way street, mathematically speaking. The SPA keeps the verifier secret, stored in memory, and prepares to send the challenge publicly. This is the foundation of PKCE's security model. Now, our single-page app sends the user over to the authorization server with a very specific request. Let's break it down. Response_type. This tells the server we're asking for an authorization code, not tokens directly. Code_challenge. That's our SHA-256 hash from step 1. Code_challenge_method. This lets the server know we're using SHA-256 for the challenge. And scope. The permissions we want the user to approve. And here's the important part. What's not in this request? There's no client secret, no sensitive data. So even if someone intercepts it, they can't use it for anything malicious because they don't have the original code verifier. In the next stage, the authorization server authenticates the user, perhaps with a username and password, and possibly multi-factor authentication. It then displays a consent screen, something like App X wants to access your profile. Behind the scenes, it validates the request by checking details such as the client_ID and redirect_URI, and securely stores the code challenge, a step that's critical for what comes next. From the user's perspective, This feels just like a standard OAuth flow, but the PKCE magic is quietly happening in the background. Once the user gives consent, the authorization server generates a unique authorization code and pairs it with the stored code challenge. Finally, the server redirects the browser back to your application, carrying the authorization code with it. This is where PKCE really proves its worth. At this point, your SPA has an authorization code, but on its own, that code is useless. To turn it into an access token, the app makes a post request to the token endpoint, this time sending along the original code _verifier. The authorization server takes that verifier, runs it through the same SHA-256 hashing and base64 URL encoding process used earlier, and compares the result to the stored code _challenge. If they match, the server issues an access token. This token is cryptographically signed and can be used to access protected resources like APIs. The PKCE flow is now complete. With the access token, your SPA can call protected APIs. Each API validates the JWT signature, expiration, audience, and scopes. The beauty is that the same access token can work across multiple APIs, as long as they share the same audience or the token has the appropriate scopes. Pro tip: always implement proper token refresh logic. Access tokens expire, but refresh tokens let you get new ones without re-authentication. When implementing this flow, always ensure that code verifiers are generated using truly secure random values, since anything predictable weakens the entire process. The verifier should be kept securely in memory only for the duration of the flow and must never be written to logs or persistent storage. Errors should be handled gracefully so that failed requests do not disrupt the user experience or expose sensitive information. Once the flow is complete, all sensitive data should be properly cleaned up. And there you have it. OAuth 2.0 with PKCE might seem complex, but it's actually an elegant solution to a real security problem. If this helped you understand PKCE, smash that like button and subscribe for more security-focused content.